All right, now watch how this works. I'm going to build a study. Okay, I'm trying to figure out if a weight loss program works. So what I'm going to do is I'm going to enlist, let's change the color of my pen. I'm going to enlist 30 individuals, randomly selected. Remember, randomization, randomization, randomization. I realize that it's not always practical, excuse me, to do that, but you really have to strive for that. So N equals 30, all right? And I'm going to put them on a weight loss regimen for 6 months, all right? And they're going to go on this diet, and it may include exercise. It may just be food. Might have something to do with who knows. It doesn't matter. All right. I'm going to give them the same treatment, and I'm going to try and figure out what their weight loss, if this program really, really works. And really, I mean, if you think about it from like a commercial standpoint, what can I claim? What if I want to market this thing? So I put them on this diet I weigh them before, put them on the diet for 6 months, and I weigh them after. And excuse me, after 6 months or whatever, let's say that the average amount of weight loss is 2.1 pounds. And the standard deviation of the sample, I just came up with this diet. I have no idea what the population standard deviation or the parameter is going to be. It's going to be 4.8 pounds. So this is pounds and this is pounds. Now, let's think about this. Why is this so big? Why is this thing so huge? Remember, the smaller the sample, the more variability there is in the data. You can get these, if it's randomized, you're going to get crazy wild swings. If you think about it, if you went out and just randomly selected 100 people, let's make it smaller, 10 people, and you tested their IQ, your standard deviation would be larger for that. Small samples produce less variability, or excuse me, more variability, right? So you would probably end up with a larger standard deviation, not necessarily, but probably end up with a larger standard deviation than the 15 points that we know is the standard deviation for IQ. All right, now let's see what we got. Remember, here's our formula right here. Let's write down our degrees of freedom right now. So just so we have them. I'm going to show you how this works. So degrees of freedom in this case is going to be n-1, which is 29. All right. I'm going to build a confidence interval. Let's go 95%. And we're going to try and figure out what the confidence interval is for actual weight loss on this diet. So if I go out and market it, it's going to end up being decent. All right. The first thing that we need, the most important thing, is T alpha over 2, just like with anything. Now, I'm going to show you how to use this chart so you know what you're doing. All right, let me get this thing out of the way. The first thing that you're going to do is you're going to identify a couple things. You're going to identify the degrees of freedom, which in this case is 29. I've got it way down here at the bottom. All right, let me see if I can crank that thing up just a notch. Perfect. Now, look at this chart for just a sec. It says area in one tail. Now, let me see if I can show you what they mean by that. Area in one tail would mean that if we were talking about a T-curve, I'm just going to refer to it as a T-curve, then the area in one tail that's cut off, which we'll use down the road, in this case would be 0.05, 0.01, 0.025, 0.05, 0.1, okay? Now, over here it says the area in two tails. That means that if I throw two tails on this thing, notice that these are the two tails or skews on this thing. It's even, so it doesn't really make sense to talk about it as skewed, but you know what I'm saying. Then the total area in both tails is equal to 0.05. All right? Now, if you think about that, what that means is what is alpha? So when you're looking at the area in two tails, what you're really looking at is these guys right here are just alpha values. So alpha over 2, or excuse me, T sub alpha over 2 is simply equal to 0.025, right? Which would be the area in the one tail. Or you can actually kill two birds with one stone because this is a stacked chart. Think of this as alpha. If they give me alpha over 2, I can use either one of these, whatever your brain wraps around most easily. Now, I'm going to follow this thing down. Let's see if I can get right on 29. Okay. Area in both tails is 0.025, which means T sub alpha over 2 is 0.025. And then I go to degrees of freedom, and I follow it across until I get to 0.025. And this is my critical value. Now I want you to notice something here before we get too crazy. Look what happens as, this thing's in my way, sorry. Look at what happens to the values as the degrees of freedom decreases. My T sub alpha over 2 is getting bigger and bigger and bigger and bigger. Now hopefully we illustrated that with this guy right here. As the degrees of freedom decrease, the T sub alpha over 2, which they refer to as the critical value, and I have in the past, has to get bigger. For us to be as confident, we have to make the confidence interval larger. This is where we're at. So once I've identified this, watch what a no-brainer this is. Oops, let's get over here and get a little bigger. Alpha, oh God, what did it say? I forgot, 2.025, is that what it was? 2.045. So when I do this, I know that T sub alpha over 2 is 2.045, and then it is identical. There is no difference. You ready? I take x bar, which is 2.1 minus 2.045 times my sample standard deviation, which is 4.8, divided by the square root of 30. And then I have 2.1 plus 2.045 times 4.8 over the square root of 30. Now I'm going to throw this onto my handy dandy calculator real quick. 2.1 minus 2.045 times 4.8 divided by root 30. All right, notice it's still root 30. It's not root degrees of freedom. The degrees of freedom are only used to figure out the value on the chart. I've seen students make that mistake, and I know it can be pretty frustrating. This is still in still goes into the formula. And when I do so, I end up with, on the left, I end up with 0.308 pounds. And on the right, if I go second entry, change my minus to a plus, I end up with 3.89. Since I'm at hundredths here, I might as well be hundredths here, even though it's 3.892. Wow. I mean, even if the population mean is here, it doesn't appear that my diet is very effective. In 6 months of using it, patients at absolute best, according to this confidence interval, at absolute best, they only lost almost 4 pounds. Half a pound a month, you know, you could almost do the same thing if you just got off the sofa and went for a walk for a half an hour. So that's how you do it. The two things that are most important for you to be able to do is be able to use this chart, which comes directly from your book, to find this guy. Because once you got this guy, life gets good. Now here's the hard part, is most computer programs either don't have a studentized T capability. It's tricky, it's harder. So this chart is actually the best way to deal with confidence intervals and dealing with the studentized T chart. Okay, we're going to do a boatload more of these things, but I do want to talk a little bit more about those assumptions that we talked about real quick. Okay, notice, if we look at what is the distribution of the population, remember these guys that we talked about? First and foremost, if we're normally distributed, I'm going to write this in, all right? As long as the population is normally distributed, we can take a sample of any size, I mean, you could take a sample of 2 if you wanted to, of any size, all right? If the shape of the distribution is unknown or not normal, then the way that we deal with that is we use a sample size that's bigger than 30. Now, why is that seems a little arbitrarily chosen? Why do we choose a value that's greater than 30? It's easy. Because that's when we are confident enough that the central limit theorem is actually going to kick in. But remember, we still have to collect these things using randomization. If we don't use randomization, we're in big trouble. What happens, let's kick over here and formalize this a little bit more. I'll put it over here. Let's do it in orange. All right, so assumptions. First things first. 1, standardized collection. Standardized. Did I say standardized before? I'll have to go back and check it out. Randomized. randomized data collection, okay? And then 2, whoops, if pop is normal, knock yourself out, any sample size, okay? Size. Number 3, if pop is normal, or excuse me, is not normal, let's throw a little tilde on there for not normal, then n has to be greater than 30. Now let's cut across over here. And if I can't get greater than 30 data values, all right, I'm screwed. I can't use parametric statistics, and I have to use something called non-parametric, which is an advanced topic. You'll actually learn about it in grad school. Non-parametric stats. Okay? And that can really frustrate researchers because it really stymies it. Okay? Okay. That's about it. That's about it. Like I said, we're going to do a bunch of these in class, so don't panic. We'll also do a bunch on our calculators where I just give you a data set and I have you build confidence intervals. Oh, by the way, let's just real quickly. If I wanted, instead of a 95% confidence interval, I do want to address this really quickly. If instead of a 95% confidence interval, because look, in this case, this was 0.05 in the 2 tails, or if you look up, remember in the 1 tail, it was 0.025 for my T alpha over 2. If instead I want to do 99%, that implies that I'm going to use 2.756. If I want to do a 98%, it's going to be 2.462. Again, I want you to pay attention to the fact that if I want to be more confident, then my T value, this guy right here, whoop, is going to grow. It's going to make my interval larger because I want to be more sure that the mean is actually inside of that interval. So to be more confident, I have to build out the interval. Okay? All right. That's enough. I'll see you in the next section.